Hello viewers and welcome to a new STM32 World tutorial video. In today's video we are going to talk about something called I2S or I2S, as someone would point out. I got a bit of flack for calling I2C, which somebody told me should be called I2C. I beg to differ. And similar, I will call this I2C. It can be I2C or I2S, I2S. So I'll call it that. It is a serial protocol, synchronous serial protocol with a clock signal, which is used to stream serial audio data or sound. It is used to drive speakers, amplifiers, etc., etc., etc. Today we are going to review an earlier video, which happens to be one of the most popular videos I ever made. Don't know why. Which is STM32 tutorial video number 15, where I generate a sine wave on the digital to analog controller using DMA. Now, the fact is, what I'm going to do today is calculation-wise more or less exactly the same. So I will strongly recommend, if you have not watched this earlier video, go back and watch that first, because that will explain the calculations in much more details than I am going to go through today. Essentially, what we're doing is we are generating a sine wave, and the only thing I'm going to say here about a sine wave is that this graphics, which is as usual on the STM32 World Wiki, you can see that the red sine wave over here can be expressed as an angular velocity or angular speed within a unit circle. So in other words, what you do is you calculate, in order to express a frequency, you can calculate an angular change that needs to happen for every sample, and that depends on the sample rate and the number of samples in a second. So that is how this frequency is calculated. The frequency, calculation-wise, is not frequency that is used, but the angular speed within the unit circle. This is all explained in much more detail in video number 15. So again, I will suggest you go back and watch this video if you haven't seen it already. Now, the reason I started looking at that is that if you have watched my last couple of videos, you will see that I actually have a couple of these discovery boards from ST, and one of the boards I have is the STM32 F407G Discovery 1. I complained about this board in an earlier video. I complained that they have this gem in the manual where they actually, if you want the serial console to work, you need to solder a couple of jumper wires on the board. It's quite insane that they sell it rather than fix them and sell some new ones, but they don't. But I have in fact soldered those wires on. It's not pretty, but it works. Another feature of this discovery board is that down here you actually have an I2S input-output. You have a peripheral that you can send this I2S data to, and then it will generate audio. It also have an amplifier and tone controls and a lot of other goodies in this little package down here. Now, that little package down here, if we look at the schematics, it is here and it's called CS43L22, and it basically connects to the I2S bus coming from the MCU, and then you will have an enable pin reset or on reset, if you like, to control this device. But you also can see here we have an I2C bus going on, and the I2C bus is used out of the audio stream to actually configure this device. You can set the volume control, you can set tone controls, you can say the number of samples that it expects, and you can see it actually have a headphone line out, and that is what you can see. My test setup, if you look at that, looks like this. We have the discovery board over to the right. I have actually plugged in a little speaker, and I have my cheap toy oscilloscope hooked up to this so we can see what actually comes out. This is all hooked up to this headphone jack, those two signals in the headphone jack and the ground, and that is all there is to this. If we look at the chip itself, the datasheet for this chip, it is linked on this page as usual. You can see here that it is actually it's a low power stereo DAC. Stereo, that is important. We got left channel and right channel. So contrary to our earlier video, we will have to generate two sine waves. So we have one in the left side and one in the right side. And that is about it. But the interesting part of the datasheet and why I bring it up is that we have our registers inside. That is where you configure this, and you can see you have quite a number of registers that ends with some volume control is here. There is how the power is controlled. You can power it off, you can power it on, you can enable and disable headphones and speakers and etc. etc. It's got a lot of settings that can be played around with. I have just done the bare minimum. So if without further ado we go in and look at our code, the interesting part is I'll go through this one at a time, but let's look at the CubeMX setup first. Now this is this MCU got a little more pins than we are used to from the STM32 F45. I usually use it's got quite a lot more pins, but the setup is exactly the same, more or less. I have set up the debug pin to include the SVO, even though I'm not using it today, and I am using an external crystal. Now the clock configuration is slightly different. This board have an 8 megahertz external crystal, and I actually have changed these values and played around with that a little bit. By default, if you let it resolve and calculate automatically, it will divide by 4, so there will be a 2 megahertz into this, and then you derive the 168 megahertz from that. But by multiplying and dividing one more time, but I wanted to have a 1 megahertz clock going over to this I2S PLL, so I divided by 8 and then multiply by a bit more here. I will get back to in a while why those changes were made like that. Let's go back to the pin configuration. You can see down here there are no analog digital, none of the analog are enabled in this. I also have no timers enabled. The only thing I have enabled is our usual serial port. In this case I'm using USART2 in our usual speed setup. We would normally use USART1, but in this case, if we go back to this photo, this is actually the USART2 pins. USART1 is hanging over here somewhere, so it was just easier to use that one. It's that simple. And that is about it. And then we have I2C. One is enabled in fast mode, so it's running at 400 kilohertz. I think this one is using the standard pins. Where on earth are they? I2C, I2C, they are hanging off here, and that is of course dictated by the datasheet and how these things are connected. In here you can see it goes to the PB6. Anyway, it is correct, otherwise it wouldn't respond. The final thing to do is to go down under multimedia and enable our I2S number 3. We are running this in half duplex because we only want to transmit. We enable the master clock output. That is the one I'm going to get back to. It is running in something called Philips mode, which is pretty much the standard for these DAC chips. We are running 16-bit data on 16-bit frames. That means each frame we're sending out to the board are 16-bit, and that is 16-bit of data. And we are running an audio frequency or sample rate of 96 kilohertz. Now, this is where it gets a little bit interesting, because you can see that we have selected 96 kilohertz, but the real audio frequency is 95.982, which means that we differ from the optimal by 0.01%. And this is where these frequencies come in. Now, please write in the comments below if you have done this and you have come up with some better values. I basically played around with this multiplier divider here, and the multiplier here and divider there, and this multiplier and this divider to come up with the best result that gives the least amount of error. But I have not found a very good way of doing this except playing around and finding the optimal values. So that is about all there is to it. If we look down in the code, we are including a library called the CS43L22. Now that is one I have created, and it is essentially just using I2C to configure this board in the optimal way of for our application. And you can see all we have in here is we have a function called CSInit, which is, look at our earlier I2C library we developed in an earlier video, and it's exactly the same principle. It's just different things. There is a CS enable, CS disable, and there's a CS master volume and a CS headphone volume. And if we go in and look at the code, it is really quite simple. We have a read register and a write register, which uses hel I2C mem write and hel I2C mem read to read and write values from different addresses following the values in the datasheet, which are these registers here. They are described in detail down here. So if you can see the power control, you can power it down, and default it is powered down, and then we can power it up by writing another value to these power flags in here. And it is as simple as that. So if we look at my init function, what I'm doing is I'm reading to verify that we can actually communicate with this chip, and provided we can, then I am basically I am enabling all the output. No, I'm actually not. You can see I did originally, but I'm only enabling the headphone now. I used to enable the speakers as well, but since the speakers are not connected to this board, that made very little sense. I'm also setting some clock selection. I am enabling and disabling some interfaces. This is all described in the manual, and using the flags up here, the big bit patterns described in these flags. And the last thing I'm doing is I'm powering it up when everything has been set correctly. I also have a volume control down here where I can control the volume. Now, one of the last things I do is I set the volume to 0, because I don't want a crack in the speaker or headphone when I switch it on. So I'm setting the volume to 0. So after initializing this inside our code, where are we? We are down here in the main. There, you see I initialize it. I set the headphone volume to 255, which is the maximum volume we can set. Now, how does this actually work? We are going to put a sine wave on this. Well, all we need to do in our code is we need to enable HAL I2S transmit DMA. In the earlier video, we would have used one called HAL, probably HAL DAC DMA or start or something like that, and it is exactly the same. You give it a peripheral ID, you give it a pointer to a buffer, and you tell it how big that buffer is. And that is all we're doing. The rest is just our usual stuff down in the while loop. We do absolutely nothing except starting this, and then it will run automatically in the background. So how does that work? Okay, first of all, up in the top here, we have some defines. We define a tau, which is 2 pi. Essentially, somebody pointed out there is a definition inside the math library where you can 2 pi's are defined in there, but that is actually doing a calculation every time. So I prefer to actually define tau here because it is a fixed value. It's 2 pi with enough decimals to not having, I mean, this is more precise than the actual calculation, so it is good enough. Then we define how many samples do we want, and we are going with 96 samples, but the actual buffer is 2 times this buffer samples because we got a left and a right, and then we need 2 full buffers so we can do the half buffer per calculation. So we calculate half a buffer each time, and then we wait for that to have been transmitted, then we calculate the other half, and so on and so forth. The sample frequency is set here. That is matching whatever we were setting in here, and we could probably go in and look at the settings in there, but it was just easier to hard code it here. We are aiming at getting 96 kilohertz sample rate. Now, once this has been enabled and provided, and let's go in and verify this in the CubeMX, up here you can see we have the SPI3 global interrupt enabled, the DMA 1 stream 5 global interrupt is enabled. So that means from the DMA handler at DMA peripheral, we will get a callback or an interrupt every time we have an event on this DMA buffer. You see this is divided into 2. The first one that will happen is this one. When we're half through the buffer sending, so we have essentially sent 96 values out to the I2S, then we will process the first part of the buffer, because at that point we start sending the second half of the buffer, so it is free to use the first half of the buffer. When we are completely done with the transmission, that means we're at the end of the buffer, then we start all over again and we start sending this part we calculated down here, and that means we are free to mess around with the second half, which we can simply point to by indexing the I2S DMA buffer pointer. Go back and watch my video about pointers and you will understand why that indexing is perfectly acceptable. Now, the actual meat is done in the process buffer, and I think you'll be surprised how simple it is. First of all, I am setting a flag if we are while we are processing the buffer, and you can see down here in my callbacks I'm actually looking at that flag to ensure that there is no overflow. If there is an overflow, I'll make a note of it so I can optimize my code better, and I'm removing that flag when I'm done with the calculation. Other than that, I'm just going through these 96 in our case, because that one is set to 96. So I'm looping 96 times, and for each of these, I'll set the buffer that we are pointing to with the I variable, and I'll set the next one as well. Now, buffer is a 16-bit buffer, so it matches directly. We can just do it like this, and you can see the calculation is basically, I take sinus of the sine function of the current angle as it is, and then we multiply by an application. That amplification is 1, so at the moment I'm not using that actually, and then we are multiplying that with the 32,767. Now the sine function can result in -1 to 1, values within -1 to 1, and that means we will get output values in the buffer of -32,767 to 32,767. After I have calculated these two buffers, I increase the angle depending on the angle change. I call it here angle velocity, angle speed, angular speed. So I just simply add, and the last thing I do down here is I check if it has gone full circle. That means 2 pi or tau. If it has gone all the way around and it is now bigger than tau, then I subtract tau from that value. So it will never get more than tau. It will always, angle will always be within 0 and tau, 2 pi, and that is all there is to it. I don't need to do anything of actually sending this out to the device. I can just sit back and look at it. Now the actual values are defined up here. We start both left and right with an angle of 0. Then in here in angle change, I set 55.0 multiplied by tau divided by our sample frequency, which is 9600, and that is the actual change per sample, right? Divided by 55 to get the exact change on a given frequency. So this will result in our left channel running with a frequency of 55 Hertz and the right channel running with a frequency of 110 Hertz. And then we have the amplification. We could set the amplification down here if you wanted to make the swing smaller, but if you look down at the init, I actually have a headphone volume as well that I can adjust here, so I could make it smaller or bigger by adjusting this value. 255 is the max. That is the highest value, the highest volume we can get out of this device. So without further ado, let's try to run this, and let's look at the output. There we go. And we can see we set the volume to 0. We can see we get 494 callbacks, and this is the full callback, this is the half callback every second. So it is a lot of these callback, but the loop value is still 17 million. So we have plenty of extra space to loop around in this while loop without doing anything. And you can see, oh, I should probably remove myself. You can see that the overflow values stay 0. That means that we have plenty of time to calculate the buffer before sending it out to the device and before doing the second buffer. Now let's have a look at the device. This is how it goes. So you can see we have a yellow and an orange. The yellow is our left, and the left is running at, I can tell you it's exactly 50 Hertz. If you look at 55 Hertz, and the right one is 110 Hertz. And I mean, just to demonstrate this, I could actually turn the speaker on. I don't know if you can hear that. Let me see if desktop audio. No, that should not make any difference. So let me try to switch this speaker on. And there you go. Okay, I don't know if you can hear that. Maybe not. Maybe not. But it does speak. Yeah, I could try to, let me try to make it a higher frequency. It might be easier to hear. I think maybe the noise cancellation. So let's do 440 and 880 hertz here. And let's see how that sounds. I need to, that actually, and we can adjust this to show it actually makes a very, very beautiful sine wave on this output. So that is pretty much it. Now, I didn't write this from ground up because, to be honest, it was a little bit fiddly to get this running. I had a strange bug for a long time I couldn't sort out, and that one was actually in my original I2C, original DAC version. I didn't have these defines exactly the same way. So I actually down here, when I initialized, where are we? Here, I actually had the wrong value out here. I had the sample number of samples times 2. So I actually ended up with the wrong buffer definition, and that took me a while because I was absolutely convinced I did something wrong up here. So that's about it. Audio output on an I2S device. Now, I plan to do a couple of more videos with this device. I think it's pretty obvious to use the SPI SD card video and add that to this so I can do an audio player. I will simply read WAV files from a SD card and play that music out on the speaker. That will probably be the next video I'm going to make. There is another thing that will be obvious to make. This discovery board actually also have a USB port down here, so we could make this a USB audio device and then throw that audio out on this DAC directly. And I thought that would be, so we can actually make a USB audio card, sound card, and I think that would be an excellent exercise to do that. So there is probably going to be 2 more videos following this one, but about pretty much the same topic. Now, another thing I want to point out here before I say goodbye is that this video is, as I said, one of the more popular videos I've done. I only do one sine wave, and I honestly don't understand why this video is the most popular, because I'm also doing another video that is not nearly as popular, which is slightly odd. Dual DAC, it is here. It doesn't have sine in the title. But this one is running 2 sine waves using FreeRTOS, and but the calculations are pretty much the same as the video we did here today. So that is about it. As usual, have a wonderful rest of the day.